Alright, hello and welcome to Chapter 10.6, Counting Principles. So today we're going to talk about three things. We're going to talk about the fundamental counting principle. We're going to distinguish between permutations and combinations. And we're going to use permutation and combination formulas to solve some problems. So first we need to start with some definitions. And that, with a little bit of movie magic, gives us our definitions. So let's take a look and walk through each of these. Again, remember, you can always pause this if you need to write these down. The fundamental counting principle tells us that the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. Okay? So if I want to know how many different ways I can order lunch, and I have a choice of 3 sandwiches, 4 sodas, and 2 sides, I would just simply multiply each of the possible options in each category. So it would be 3 times 4 times 2. We'll look at some examples that should make that a little bit more clear. A permutation is an ordered arrangement of items where no item is used more than once, and the order of arrangement matters. Okay? The formula we're going to use here is in red. It looks like this N with a big P in the middle and an R. The way we would say that is the number of permutations of N things taken R at a time. Or we could think about this as the different ways to order a set of R things from a selection of N total things. Our formula is going to be N factorial, right, the total number of things in the numerator. And then in the denominator, it's N minus R factorial. Let me make sure that's clear. This is an exclamation point. So the numerator is the total number of items factorial. The denominator is the total number of items minus the number we're choosing factorial. We also have a combination. This is when we select items from the same group. And again, no items are used more than once, but the order of arrangement does not matter. The way we can think about this is the number of possible combinations if R items are chosen from a group of N total things. Here our formula is in blue. It is N factorial divided by N minus R factorial times R factorial. One of the most complicated, tricky things in this unit is figuring out when am I dealing with combinations and when am I dealing with permutations. The big idea here, the big difference is, does order matter? Here's an analogy I've used in the past that makes maybe will help you make sense of this. So here I have two different forms of ice cream. Right on the left I have a bowl of ice cream, and on the right I have a ice cream cone. So on the right here we have a permutation. Why is this a permutation? Well, the order in which I get an ice cream cone matters. I want strawberry on top, chocolate in the middle, and mint on the bottom. If that order was changed, that's a different ice cream cone, right? If you eat chocolate first, then mint, then strawberry, that's different than the original permutation. The order does matter. That makes it a permutation. On the left, we have a combination. The order doesn't really matter when I have a bowl of ice cream, right? I can just move the bowl around, and then the mint is in the front, and then I could rotate the bowl, and now the chocolate's in the front. It didn't really matter. The order doesn't really matter when everything's flat like this. So maybe that'll help. The big question we need to ask ourselves with combinations and permutations is, does order matter? Okay? So let's look at a couple examples. Here they are asking us to work through a permutation problem. So we have the formula we're going to use is our formula for permutations. It's going to look like this. It's going to be 6 factorial divided by 6 minus 3 factorial. And once I simplify this, I'll get 6 factorial divided by 3 factorial, which is the same as 6 times 5 times 4 times 3 factorial divided by 3 factorial, which I can simplify by canceling those 3 factorials, and I get 6 times 5 times 4, 120. What does that mean? There are 120 different permutations when I'm choosing 3 items from a set of 6. Let's work through example number 2. Here, all that's different is that I'm now using my combinations formula. So I'm going to set that up. It's going to look like 6 factorial divided by 6 minus 3 factorial times 3 factorial, which once I simplify, I can write as 6 times 5 times 4 times 3 factorial divided by 3 factorial times 3 factorial. As you can see, one of our 3 factorials will cancel. This will equal 120 divided by 3 factorial. 1 times 2 times 3 is 6. And once I simplify, I get 20. What that 20 represents is if I have a set of 6 items, there are 20 different ways to choose 3 of those items where the order doesn't matter. So we're going to get into the examples. I'm going to work through every single one of these. I would really recommend trying these first. What I find with these problems is that there's a few different paths we can follow, and it's worth taking a shot at them before you see us walk through them. Okay, so I strongly recommend trying as many of these problems as you can and using these notes as more of a check for understanding. All right, let's take a look at example 3. So here we have the situation where a pizza can be ordered with 3 choices of size, small, medium, or large, 4 choices of crust. We have thin, thick, crispy, regular, and then we have 6 choices of topping. How many different one-topping pizzas can be ordered? Well, I really need to think about how many different of each option do I have. Well, I have 3 different sizes. I have 4 different crusts. And I have 6 options for one topping. So what this represents, the product of this will be for each size option, I then have 4 options of crust and 6 options of topping. I can think about it. We won't do the whole thing, but as like a branching tree, right? I have 3 options for size, and then on each of those I have 1, 2, 3, 4 options for crust. 1, 2, 3, 4. 1, 2, 3, 4. And then off of each of these I'd have 1, 2, 3, 4, 5, 6 options for a topping. The counting principle allows us to take the options for each and multiply them together. So 3 times 4 is 12, times 6 is 72 different options for pizza. Moving on to number 4, we're taking a multiple choice test that has 15 questions, and each question has 4 choices. How many ways can we answer these 15 questions? Well, I really have 4 choices on question 1, 4 choices on question 2, up to 4 choices on 15. The way I can write this a little bit more succinctly will be 4 to the 15th power. So your odds aren't very good when you're taking a multiple choice test of guessing everything right. There's a lot of ways we can answer these tests. All right, so let's move on to example number 5. Here we're looking at the telephone number options in the United States. So telephone numbers have a 3-digit area code followed by a 7-digit local telephone number. Area codes and local telephone numbers cannot begin with a 0 or 1. So there's a few ways we can do this. We really have, so here's the way I think about it. Right? We really have 3 slots to fill with our area code, and then 7 choices, 3, 4, 5, 6, 7. 7 slots to fill, with our local telephone number. Well, I also know that I can't begin with a 0 or a 1. So what I need to figure out is I need to figure out how many different options do I have in each individual slot. So the area code cannot begin with 0 or 1, but it can begin with any number from 2 to 9, which means I have 8 total options here. I have 10 options on the 2 subsequent slots. I also know that the local number cannot begin with a 0 or 1, so I only have 8 options there. And then for the rest, I have 10 options, right, 0 through 9. I can write this a few different ways. I think what might make sense is it's 8 squared times 10 to the, well, we had 2 here and 5 here, so what is that, 10 to the 7th? Sorry, that should be 10 to the 8th. So I had 2 here and 6 here. That's a pretty big number. If we were to plug that into our calculator, I think we end up with 6.4 billion. Total number of phone numbers in the United States. All right, let's keep moving. Here, number 6. How many ways can 6 books be lined up along a shelf? What I need to figure out, does order matter? Well, it must, right? Because if it didn't matter, I'd just have 6 books on a shelf in any order I like. So I really like this thinking about slots idea. So really I have on the shelf, I have 1, 2, 3, 4, 5, 6 places to put a book. In the first slot, I have 6 choices, any of the 6. In the second slot, whatever book I put first is no longer an option. So now it's 5 times 4, 3, 2, 1. Really, that's going to be 6 factorial, which when I evaluate that, I get 720. Moving on to number 7. You're the coach of a Little League baseball team. There are 13 players on the team, and you need to choose a batting order of 9 players. How many different batting orders do you have as an option? Well, again, we can think about this. I want to try to draw the connection between this slot idea that I've seen in the last couple examples and our formulas. So I really have 1, 2, 3, 4, 5, 6, 7, 8, 9 slots to fill. And then I have 13 options for the first player, or for the first spot, 12, 11, 10, 9, 8, 7, 6, 5. Well, as you can see, multiplying all these numbers together can get a little messy. I can use my permutations formula. I'm going to use permutations because order matters. And I can write this as 13 factorial, that's our n value, divided by n minus r, which is going to end up as 4 factorial. And we can kind of see where this is coming from, right? This is the same as 13, pick 4. We can see that we would have 13 factorial, except that we don't use our 4 through 1 here. We would divide by 4 factorial. When we evaluate that, we get an extremely large number. That is 259,459,000 different options. Oh, sorry, there should be a 200 here. Just as a quick aside, I'm going to post a video on how to use our calculators to determine combinations and permutations. Look forward to that later on in the week. So let's keep working through the last few problems here. The big question on all of these final problems is, does order matter? So On number 8, I have a group of 10 physicians. How many ways can 4 people be selected to attend a group conference? Well, in this case, order does not matter. Order doesn't matter because any group of 4, there's no dedicated roles for those 4 people, right? Me, Mrs. Johnson, Miss Charles, and Mr. Schiller all going to a conference is the same no matter which order we listed those names, right? So the order doesn't matter. So all I need to do is use my combinations formula. I'm going to say this is 10, choose 4, which is going to look like 10 factorial divided by 4 factorial times 6 factorial. And when we evaluate that, there are 210 different ways 4 people can be selected from a group of 10. For number 9, we are looking for a 3-person committee needed to study ways of improving public transportation. How many committees can be formed from 8 people on the Board of Supervisors? Well, again, order doesn't matter. It doesn't matter because that 3-person committee is there's no difference between each role in the committee, right? So again, I'm going to use 8 and we're going to choose 3. If I were to write this out in my formula, it would be, oh, sorry about that. It will be 8 factorial divided by 5 factorial times 3 factorial. One thing you'll notice on combination problems is our denominator, those 2 factorials will always add up to our numerator value. It makes sense, right? It was n minus r factorial times r factorial. They will always add together. And the nice thing is, since we're multiplying these 2 factorials together, as long as I know one of those numbers, the opposite is the difference between the total number and the number of people being selected. One way to think about this is selecting 5 out of a group of 8 is no different than selecting 3 out of a group of 8. They're going to end up being complementary totals. So anyway, once we evaluate 8 factorial divided by 3 factorial times 5 factorial, we'll find that there are 56 different ways to choose a 3-person committee. All right, last 2 here. In a race in which there are 50 runners and no ties, how many ways can the first 3 finishers come in? Here the order does matter, right? There's a difference between first place, second place, and third place. So I can write this as 50, pick 3. And if I were to evaluate that, it would be 50 factorial over 47 factorial. The other way we can think about this is how many different people can finish first? Well, there would be 50 people in first. Once there's a first place finisher, there's 49 remaining runners that could finish second and 48 that could finish in third. So either way, we could say it's 50 times 49 times 48, or using our permutations formula, 50 factorial divided by 47 factorial. I think that will be a total of 117,600. And finally, on number 11, how many ways can you select 6 DVDs from a list of 200? Here our numbers are going to get unwieldy. So we're going to say, well, does the order matter? Nope, 6 DVDs are 6 DVDs. I'm going to use 200, choose 6, which is the same as 200 factorial divided by 194 factorial times 6 factorial. Which, once we evaluate, we get something around 82 billion. Which is why these counting principles are valuable, right? There are too many ways. We're not going to sit here and count to 82 billion. We need a shorter, succinct way to doing this, And the most straightforward way is going to be through using combinations and permutations. Nice work, everyone.